dark matter search in Jinping, a mountain in Sichuan province in China. So this summer they have obtained the most stringent dark matter search. Well, Jiang Lai Liu has played a very important role in both experiments. So he received the Outstanding Youth Prize in China this year or last year?
2015.
2015. So that's one of the very prestigious prizes in China. So we are fortunate to have him have this window this afternoon to give the colloquium. Let's welcome Professor Jiang Lai Liu.
Thanks a lot for Professor Liu's kind introduction and also the invitation for me to come here. I also thank Bob for organizing this diabetic meeting. I know that's a lot of job, a lot of work. I did it 4 years ago, and it was a lot of details. Anyway, so Bob and I are long-term collaborator on diabetic, as Professor He said, and today I'll talk something somewhat similar to neutrinos, but something that we have even little less idea what they are. So the title of the talk is Deep Underground Xenon Observatory. So deep underground means that this laboratory that we're working with is very deep under the mountain. So that bay, just to give you an idea, is 400 meter overburden. That's our experimental far side. And this place is a factor 4 even deeper, okay? 5 deeper. And so, and we're using, in this experiment, xenon as the target and also as a detector. So this is not in a very developed region in Guangdong area, but in a really remote area in Sichuan province. And that area is totally different from what you could imagine from a big city like Beijing and Shanghai. So the name of the experiment is PandaX. Panda is the symbol for Sichuan food. Anyway, so this is where we were, and this is an experiment that will be doing experiment on both this unseen dark matter as well as studying the basic property of the neutrinos. So let me now come to this probably familiar picture showing the biggest mystery in my mind about nowadays universe, which is that we know a lot about the world made out of proton and electron that us are made out of. And ironically, this ordinary matter is only 5% of the entire energy and mass of the entire universe. And the rest are a big part, 27% is the unseen world. We don't know, unobservable dark matter. So they don't make light, they have no electromagnetic radiation. And the other, also ironically, another 68% is so-called dark energy, which is not really an energy that you could use to power your light, but rather a very strange accelerating expansion of the universe. Can be somehow parameterized as a term called dark energy. So these are the two biggest mysteries. I think the dark energy is perhaps even more remotely connected to the ordinary world. Dark matter, we think they are really matter, meaning that they do have gravitational, like they have this standard Newtonian gravitational interaction. They're matter, but we don't know what they are made out of, microscopic. I probably don't have to go through all the very strong evidence showing that indeed this matter do exist in our universe. There are a lot. Overwhelming evidence from both the cosmic wave background fluctuation, the large structure formation, the rotation curve of the galaxy, to the gravitational lensing measurement, also when the Hubble measurement of two galaxies sort of going through each other. All these and many of the others evidence linking together just a single picture that the universe is full of these gravitational attractive dark matter. They are diffusive, but at the same time, at large scale, they do form lumps. Okay. So the way to think about our own galaxy is that you see this disk, which is our own galaxy. But in order to make such a large rotating structure, to make it possible, the gravitational energy given by all the observable matter is not enough to have this large thing rotating as fast. Rather, what you need is to have this thing being surrounded by a big fog, which is the so-called standard halo of the dark matter, in order to explain how our galaxy rotates. And how much is that dark matter in our room, for example? It turns out that this density is very, very little in the ordinary sense. If you take a milliliter of the volume and ask what's the energy of this dark matter using E equals mc squared, it turns out that this dark matter inside the 1 milliliter is only 1/3 of the proton's mass. So why do we care? Well, the reason is that such a small density in our ordinary sense, once they form into a galactical scale, and then it could change the galactical motion of the galaxy and so on drastically. Okay? So, let's see, let me move it down. Okay. So, of course, I mean, macroscopically, these are all gravitational behavior, which has been known for years from the astronomers. But physicists like to understand the microscopic nature of such a thing. And at least from everything we know, an animal, a cat, a human being are made of these microscopic elementary particles. So we would tend to think that this lumpy, full of universe matter has to have some microscopic structure, or made out of elementary particles, the other word. There are many, many theoretical models. There's a lot of theorists here, and then there are a lot of theories explaining this. But I was just focusing on the most quote-unquote popular theory, which says that this is a elementary particle that might persist weak interaction. They're called WIMPs, or weakly interacting massive particles. But these are not the weak interacting particles that we know. These are some additional weak interacting particles beyond the current knowledge of the elementary particle world. One good attractive point for this model is that naturally it explains why, from the birth of the universe, why till today we explain the observed dark matter density in our universe. And the other good consequence about this is that if such a particle contains weak interaction, in addition to gravitational interaction, then maybe we have a hope to actually do a terrestrial experiment to measure such a particle in the laboratory. So, in general, there are many different. There's 3 different methods to make such a measurement by human beings on top of the observation. So the so-called direct detection is what I'm going to be focusing on, looking at these particles scattering with ordinary matter, and we detect the recoil signal from the ordinary matter. There's another way, which is called the indirect detection, which is that if you look at something where there's a lot of mass, for example, the center of galaxy, or you could have particle, anti-particle of the dark matter annihilating, generating high energy ordinary matter, and then you detect these high energy ordinary matter in order to detect this. And one of the satellites which was launched last year called Wukong, I don't know, there's another English name called Gant, that was actually specific for this. Another more famous one is the Santing's AMS-2 satellite, trying to do this type of indirect detection. The third one is also kind of well known. You try to generate a lot of energy density at LHC, for example, colliding ordinary matters, and then you look for missing energy. And if there are missing energy above what you expect from what we know, then this missing energy might be, the dark matter might be responsible. So let me now focus on the direct detection, because I think that actually is more something that even a small-scale experiment can handle, and it's also easy to explain. Now, I mentioned that this the standard halo model says that our galaxy is enclosed in this very massive halo. Assuming that, not assuming, we know that our galaxy, our solar system is rotating in the galaxy with a speed of about 200 kilometers per second speed. So this is nice because it generates a relative speed between our Earth to this galactic halo. And if the halo is made out of these elementary particles, then you get actually a free beam coming through. So therefore, you only have to set up a detector to detect such the recoil particle generated by this dark matter beam. So the so-called direct detection is, you have detectors sitting in this beam and they're looking for the recoil signal. For technical reasons, this is actually a classical measurement because the dark matter is moving with really a classical speed. So you're really looking at a 2-particle M1, M2, and looking at this collision. Okay? High school student can do this kinematics. It's very simple. Now, for the reason that it's a little technical, we think that this massive, so-called massive particle is of the order maybe 100 GeV, 100 times heavier than proton, for the reason that somehow it is naturally being predicted by the particle theory beyond the standard model that they have a mass closer to the W and Z particles. If this is true, then thinking of this M1 and M2 collision, you would like to have your target to be sort of the same mass as your projectile, so that you could actually get the maximum recoil energy for it to be easy to detect. Therefore, it's natural to use the atomic nuclear as the target to detect, because that will give you the maximum energy. There's actually no reason, if you have an ordinary matter, that the dark matter would not scatter its electron. It will do. But because the mass difference between the electron and this 100 GeV is too large, if they scatter, you don't see it. Okay? Therefore, when we say dark matter detection or wave detection, we always talk about some nuclear kicking out. That's the signature. It's not because dark matter only scatters its atomic nucleus. Okay? So here are a summary of a few popular targets that people have been using them to use both as a target and detectors. For example, germanium, argon, silicon, and xenon. Let me just focus on xenon. Xenon is a target which has a charge number 54 and a mass number about 132. Okay, so it's pretty large. Now, this is a typical recoil spectrum from the dark matter. So one thing you do notice is, as a function of recoil energy, one thing you notice that it's essentially featureless. It's just an exponential form. Okay, there's no peak. Okay, that's bad for detection. It's similar for the other targets as well, all exponentially falling. The other thing is that for the xenon feature is that as you're going to higher and higher recoil energy, essentially the dark matter particle is transmitting higher and higher momentum to this atomic nucleus. You start seeing some of the substructure of the nucleus. And therefore for the xenon, it turns out for higher recoil energy, this you started seeing a so-called form factor effect, okay? Because you're seeing the substructure. That's a detail. In any case, this is assuming that the dark matter is 100 times heavier than proton, assuming given cross-section. Now, the other thing is, because this dark matter particle is non-relativistic, it will view this entire nucleus, if you ignore the form factor, it will just view the entire nucleus as a same thing, okay? a single ball. In this case, there's actually a atomic number squared effect, because this is a coherent scattering. Therefore, you know that in order to have a very efficient detection, you would like to have something heavy, so the A squared is large, to give you this enhancement in the scattering rate. Okay? Just give you a scale of the energy scale we're talking about. For this type of scattering, the energy scale is a few tenths of keV. So this is about 100 times smaller energy than that we use to detect the reactor neutrino, in which case we do MEV measurement. This is tens of keV experiment. So therefore, lower energy, featureless energy spectrum makes such a detection very tough. Also, because of the weak interaction nature, this is similar to neutrino detection, that it's very weak, the stacking rate is low, so additional toughness for such an experiment.
So only Xena has that kink?
You mean this thing?
Because you have a form factor and also
The form factor turns out to be more important for it because it's a fatter nucleus.
looks like there's a kink.
Which one? This is probably a drawing effect. I think this is a drawing effect. But I mean, this one's, you're seeing more structure from the xenon nucleus because it's just large. Okay?
Not for
Argon, yeah, it's much smaller. Yes. Okay. So, so where are we with the dark matter detection? So this is an entire program started in '85. Edward Witten was actually the first one to propose such a direct detection, and it took more than 30 years until we get to this point. The sensitivity of the experiment has been growing exponentially, but still nobody has really convincingly observed dark matter particle interaction. Okay, but at this moment, the Xena experiment has carved into the mainstream supersymmetric model parameter space. So let me try to explain this figure just a bit. The y-axis here is the scattering cross-section, more accurately, the spin-independent scattering cross-section between the dark matter particle and the nucleons, neutron or proton. It's the same. The x-axis here is the mass of the dark matter. Okay. So what's shown, a curve on this figure is an exclusion figure showing all the parameter space above these curves are vetoed or disfavored above 90% of the confidence level. One thing that you notice is the scale of these exclusion figures has already been of the order 10 to the minus 45 centimeters squared. And this is an important number. If you do actually neutrino, you know that the neutrino, which weakly interacting with the neutron and protons, the cross-section is of the order 10 to the minus 40 some centimeter. Okay? So it's interesting that nowadays, these exclusion, in particular set by the Xena experiment, has already get into the region where the weak, sort of this typical weak interaction prediction. Okay? And all these circles, we are not really experimental result. These are the SUSY supersymmetric model prediction, but being constrained by the LHC-11. So these are the surviving sort of phase space after the LHC-11. Okay. Like I said, there's no convincing candidate, but I think it's the job of the next phase of the experiment to try to clean this area up. Ultimately, this detection is actually limited by the fact that we are also bombarded by the solar neutrinos. Therefore, when you have a detector large enough, at a certain point, you start seeing these neutrinos coherently scattering with your target, which you cannot reject as a background. And so this golden dashed line is the ultimate limit from these direct detection. In which case, all the dark matter physicists will become the neutrino physicists once again. Okay. So let me now talk about the xenon experiment in a more technical form. What we see, xenon is the second heaviest noble gas. Okay, and when you liquefy it at negative 100 Celsius, the density is a factor of 3 compared to water. So liquid xenon is the major detection target, but this type of the detection technology is called the dual phase xenon. So we not only use the xenon, we also use a little bit of the gas. Use the gas and liquid interface a little bit. The pioneering experiment is in Italy called Xenon 100. And this was actually not a 100 kilogram, rather a 40 kilogram detector, or fiducial mass detector. But this is actually the experiment that defines that the liquid xenon is a very, very attractive target for doing such an experiment. This is the first one that demonstrating the scaling up is relatively simple for using this technology. And they ended in 2012 setting the limit. Right now they have a ton scale experiment which is under commission, not really started taking data yet. The follow-up experiment is in the United States called LUX, which is, they say 220 kilogram, but it's rather, this is a sensitive volume. The actual target is only 100 kilogram-ish. And this is actually just finished running. This is the, and they also had very tight constraints. And their next phase called the LZ project, which is a multi-ton version of the this experiment is in preparation. Now, the major advantage for dual phase xenon is several folds. It's a combination of a large target, making it easy to scale up. A low energy calorimeter means that all the energy carried by this recoil nuclear gets absorbed in this detector, very similar to the neutrino detector, a low energy neutrino detector. The other very attractive feature is that it makes 3D reconstruction of a vertex. You're taking a picture of where the event happens. For various reasons, it's a very powerful, it has a very powerful background rejection, which I'll get back to in just a bit. Lastly, because the density is high, its density is 3, therefore the outside of the xenon body is shielding the inside of the cleanest region of what we call the fiducial mass. So making this so-called self-shielding a very, very important feature. So here are some diagrams illustrating how this detector works. I mentioned there is a liquid phase, which is the main target for the detector. Essentially, you have a basket full of liquid, okay? And you instrument the top and bottom with PMPs, very much like a neutrino detector, very simple. But at the very top of this liquid, you have to have a liquid and gas interface. And what you do is to apply electrical field along this liquid. Therefore, if you have some interaction inside this liquid, the electrons being knocked out by this interaction can get drift along the electrical field into the gas region. Now, initially, the interaction happens. It makes the first initial flash of light. Gets detected by these photomultipliers. And then the drifted electron, because the drift speed is of order millimeter per microsecond, once the delayed electron gets into the gets gaseous, there is actually a stronger electrical field to amplify the signal. Therefore, you have the second flash of light. The amount of the light is proportional to the number of electrons that you are drifting. Therefore, you have basically a prompt S1, we call S1, and delayed S2 light. And both, the amount of the light is proportional to the energy. By looking at the timing difference between these two flashes of light, you do know the vertical location of this interaction. And then remember, this PM photomultiplier are allocated in array form. Therefore, the XY positioning can be determined by looking at the pattern from these PMPs. That's why we call this as a 3D reconstruction of the vertex. The other important feature is that if something like a background can scatter several times in a detector, in which case you should have actually two different electron clouds being drifted upwards. Therefore, when you look at these S2 signals, there should be multiple. Okay? Therefore, such multi-scatter events can be easily rejected by this technique. Okay, so I mentioned that such experiment is difficult because the weak interaction is too weak, so the signal is low. What makes things worse is that on the surface of the Earth, we are bombarded by a lot of stuff. We're bombarded by gamma rays from the long-lived radioactivity in our environment. At the same time, we're also bombarded by the cosmic rays, okay, generated in the outer space, but penetrating into the atmosphere, generating all the secondary stuff that makes basically any experiment on the Earth insensitive, blind. In order to shield from such a radiation, the best place to do such an experiment is underground, so that you use the body of the mountain to shield us of all the Earth, to shield the cosmic rays. But shielding the cosmic rays is not sufficient. You also have to get rid of all the gamma ray background surrounding the detector. Therefore, in all these underground experiments, the detectors are heavily shielded by a lot of stuff in order to stop the gamma rays. So this underground lab in China is, like I said, located in a very remote region. This is Sichuan province. If you know this red dot here is Shanghai. This is Taiwan. So Sichuan province, the south of Sichuan province has a lot of mountains. And this is sort of between the transition from the flat region to the Tibet plateau. Okay? A lot of mountains over there. That's essentially where the underground lab is located. In this region, there's a branch of the Yangtze River called Yalong River. Okay? So it runs from a little north west to the southeast. Okay? A river goes this way, and then in this region, which is actually dominated by the E ethnic group, this is a region that's very, very remote. There's a mountain called Jingping Mountain. So the river actually makes a U-turn, okay, in this region. It turns out this river has very, very rich hydropower. Therefore, starting from 2006, the government decided to build a very, very powerful hydropower plant, building a very huge dam, 300-meter dam, huge dam, across the river, just to generate hydropower. And this dam was completed in 2015, started generating electricity. It's a huge one. It's actually the tallest dam in the world now. In any case, in order to build such a dam in this very remote area, they have to transport all the concrete, all the steel, and all the stuff over there. In order to save money, not to have to go through the mountain road, the company actually dig an entire tunnel through this mountain for transportation. So 2008, this mountain was, this tunnel was completed the day when the Olympics started. Okay, it was this was when the tunnel was completed. And then a bunch of physicists noticed this place, and that was the time when dark matter was sort of, there are actually a few suspicious events, being observed somewhere else. So people really get excited, saying that we really have to have an underground lab in China in order to do this dark matter detection. So a year later, this company, before they actually retract all the civil workers, basically they donated this a very small experimental hall to us. And this was the underground lab ran by both Tsinghua University and also the hydropower company. And Shanghai Jiang, the group led by this PandaX experiment, was the second experiment that landed into this underground lab. By depth, this mountain above this lab is 2,400 meters. Okay, so this is actually much deeper than even the snow lab. So it's the deepest underground lab in the world. Okay, so now let me move on to the experiment. The name of the experiment is called PandaX, and it's not just because it's in Sichuan we have to give a panda, but rather it's several names: particle and astrophysical xenon experiment. That's the acronym. The reason we gave such a strange name is also because at the beginning we wanted to do both the dark matter detection as well as doing a double beta decay experiment, which I will comment at the end of this talk to understand the nature of the neutrinos. So we developed this experiment in a phased form. Starting from 2009 to 2014, we developed the first phase of the experiment. It's a 120 kilogram dark matter experiment. And after that, shortly after that, we upgraded the detector to a 500 kilogram detector. So we call PandaX2. And we envision this experiment we will continue to run until 2018. And after this, we will actually upgrade this detector into a multi-town xenon detector. We call it PandaX X-town. And the timeline for this is not entirely clear, but we think we can probably start assemble the detector by 2018. And at the same time, in parallel, we're developing another program called PandaX3, which is using rather a high-pressure gas xenon, not a liquid xenon, to look for neutrino-less double beta decay from xenon 136, which I will comment at the end. This is a very small collaboration in comparison, for example, other collaboration that this institute is involved in. We have about 50 people. And now the collaboration is growing. We have 8 institutions now in China and a number of them overseas. So one important milestone from this experiment is that the entire equipment gets moved to Jinping in summer 2012. We have everything in crate, spent a very long time assemble everything and making sure everything worked. It was very lengthy. In the end, the detector looked like this. You don't see the detector, by the way. You see the shielding. So everything you see here, this is 3.5 meters across, are all polyethylene, lead, polyethylene, copper, and all this shielding. And this inner copper cylindrical thing is what we call the vacuum jacket, and also a shielding for the cryostat, because liquid xenon has to live in negative 100 Celsius environment. So the detector is actually inside. Let me first show you the results from PandaX1 just to motivate you. This is one result that we published in 2015. Okay, once again, all the curves on this figure is exclusion plot as a function of the cross-section versus the dark matter mass. The red line is the exclusion by PandaX1. Okay, so we were not competitive except at the very low mass. For very low mass, a few times heavier than the proton, we are okay. But one important thing is that at that time, there were still a few sort of quite controversial claims from other experiments, which are shown by these groups. Okay, so we had one experiment that essentially disfavored strongly all these controversial claims, and so at least that's the first demonstration that we could do something. So very quickly after Panda 1, we started with the upgrade. The detector now